All right. Hello, everybody. Welcome in to the last Coiled webinar of the year. I'm Christiana from the Coiled team, and I'm here with Gus today. Hey, Gus.
Hello, Christiana. Hello, everybody. Thank you so much for having me. Really happy to be here.
Thanks so much for joining us. So as you can see, today we're having Dask in the Wild, how customers use Dask, hosted by Coiled's very own Gus. And we're going to get started in just a couple minutes here, but we'll give folks a few more to join in. If you're joining us, we'd love for you to introduce yourself in the chat. Tell us where you're tuning in from. And when you are typing in the chat, make sure you send that to everyone, not just hosts and panelists. Otherwise, me and Gus will be the only ones to see it. But yeah, welcome. And I believe Gus has a question to start us all off.
Yeah, in the spirit of maybe a recent AWS outage, my question to the team, and oh, hey, Sammy, I see Sammy in the chat. Good to see you, Sammy. What was your least favorite cloud experience or cloud service in 2021? So I think what was it, maybe a week ago or 2 weeks ago, there was this big AWS, US East 1 outage. We love AWS, we love GCP, we love Azure, but working with them can sure be frustrating in a lot of different ways. And so why don't you go ahead and share yours in the chat? I think mine would be tied for somehow the console and other things, any AWS service being tied to US East 1. So with that region down, nothing worked. That was a great one. Maybe EKS spin up times are yours, but go ahead and drop those in. Hello, we got Matt Allen from Tucson. I love it. Matt from Raleigh. Hey, I'm in Winston-Salem, Matt. So, I mean, I guess maybe you're in a cooler part of NC, but I like where I am too. So, Faisal from Denver. Awesome. Hello, hello.
Amazing.
Yeah. And just as an aside, since I see, and I hope I'm saying Sammy correctly, but the reason I know his name is I recently posted something on LinkedIn. I was giving away a copy of a book, and I want to actually grab that. Giving away a copy of this book from the last webinar we did, the previous Coiled webinar called High Performance Python, written by Ian Oswald. And I was offering up 5 copies of this book to anyone who sent Ian a message with something that they wanted to learn about high performance Python. And only one person took me up on that. Only one person sent me a message, Sammy. So unfortunately for Sammy, not unfortunately, he's getting a book. I don't think it's arrived yet because I shouldn't reveal where he lives, but it's being shipped to him. If he lived in a place that was 2-day Prime accessible, he would have gotten it by now. Not arrived yet, Sammy. Okay, yeah. So if you, so by the way, that also means there are 4 copies of this that I budgeted for that I will send to you. So all you have to do to get a copy is, Ian loves this, by the way. Ian, he doesn't work for Coiled, right? He does his own thing. He's a big part of the PyData community. He's a great guy. He loves when people share message with him about stuff they've learned from him or want to learn. So something you want to learn about high performance Python, this is the guy. Send it to him, and then just, send me an email, send me a screen capture of what you sent to him, and send me your address, and I'll ship you a physical copy of the book if you like. And there are 4 spots remaining.
Absolutely.
So,
Moral of the story, give Gus a connection on LinkedIn, because he posts some awesome content and awesome giveaways. So if you take away one thing from our webinar.
I was gonna say, I can't even give stuff away. I'm sure people, there's some trick. There's no trick, I promise.
Yeah.
I'm not that clever.
There's no catch. Awesome. Okay, well, I think that we can go ahead and get started. We've got a lot of folks that have since joined. So if you're just joining us, feel free to introduce yourself in the chat. Tell us where you're tuning in from. But I think without further ado, Gus, you can take it away. And again, you can feel free to ask questions as you're listening to Gus in the chat. Just make sure you set that to everyone so everybody can see them.
Yes.
But yeah, Gus, thanks for being here. Let's do it.
Thank you, Christiana. Yeah, let's do it. So thank you, everyone. Today's presentation is Dask in the Wild, how customers use Dask. And I want to introduce our topic, explain why I'm the one presenting this, and offer a few initial disclaimers. But I hope today should be, next slide, there we go, should be a lot of fun. We're going to cover, you're going to walk away from this with hopefully having covered 3 key things. First, we're going to build some fast but important intuition around parallel computing with Python. This is necessary for these examples to make sense. Then the meat of what we want to present today, I'm going to share use cases from financial services, life science, and energy, specifically oil and gas. And I want to share some of the business context here. One of the things I find missing often from a lot of the great and wonderful Dask examples and tutorials is like the actual business domain, the things that make this relevant to a person who is working in one of these fields, not just for people who are software engineers who are, reading in a bunch of Parquet data and doing a big join, which is applicable across everything. And then, hopefully we'll have some fun here because I'm planning to demonstrate these examples. I've got my Anaconda hoodie on, I've got my Coiled mug, like we're going to show some code, we're going to run some of this stuff live. I'll share links for things that you can then run on your own. And hopefully you can see this, you can see things running, hopefully it will make sense. I do have a very, very important disclaimer. So I'm going to be sharing by the way, why am I giving this and this disclaimer? So I work in sales for Coiled. This is not a sales presentation, but what this is I'm privileged to talk to people every day who use Dask in a variety of different environments for a variety of different use cases. You can maybe guess what 3 industries are most represented: financial services, life science, oil and gas. For conversations that I have, if you ever have a conversation with me, that will remain privileged, maybe except the thing I shared about Sammy in the book. I figured that was public, right? But anything else is private. I'm not going to share anything from those conversations. Coiled customers, Coiled people involved who talk to us, lips are sealed. I will, when I share a specific company name or specific individual, these are publicly available. And I don't want to imply, in no way am I implying any relationship between Coiled as a company and people who are using Dask and who've shared public examples. But I'm going to use those public examples and overlap them with the stories that I hear day in, day out about common usage patterns for parallel Python, for Dask, across these industry examples. So if that makes sense, right? Nobody when you hear names, you hear companies. I'm not saying that they have a relationship with Coiled. I'm saying that they have shared publicly how they use and deploy Dask. But these are real stories. These are real things that I hear. I'm, again, very privileged to hear all the time. And I want to try to connect the dots between generic, parallel Python stuff, maps and apply, submit, and then, running something like a Monte Carlo simulation, or looking at well logs and seismic data analysis, or doing cell segmentation. I want to tie these together. Okay, and then finally, kind of the last note of brief introduction here is like, if you leave this webinar with nothing else, this is what I want you to know, or this is the kind of the key idea. These specific industries, plus a bunch of others, have 2 big trends going on that are relevant for you all here. Large increases in data volumes, no surprise, but I don't even know if everyone really grasped how big this is. And then increasing Python adoption. This is critical. Python is this wonderful tool. Hopefully, if you're here, it's because you like Python. Python works really well, single core data sets that fit in memory. It doesn't work great on bigger data sets. What Dask does is it scales Python to large data sets. So why does that matter? Well, if you learn Dask, you can apply existing code to large data sets. This is the key. This, I think, is the critical thing. And I'm going to try my best to hammer this throughout the examples that I show. You can build really cool things in Python. And if you're the kind of person who can do that, good for you, go forth and conquer the world. If you just want to copy what somebody else does with permission, but if someone in your organization has built something really cool in Python, if you have a tool like Dask, you can now grab that existing thing and you can scale it. I'll even show you an example later where we're going to scale something that isn't Python, just a random executable, and we're going to do it with Dask. This to me is the most exciting thing as someone who's not an engineer, who's not a creative, I'm not building stuff, but I can take something that works and I can scale it, like a kind of like a VC model, right? That's so everyone's a VC these days, it seems, at least it seems that way on LinkedIn. They're like, oh, find something that works and scale that thing. Well, actually, we're going to do that with data analysis, maybe with machine learning, with any sort of quantitative method. We're going to find something that works. We're going to apply Dask. We're going to scale the heck out of it. Okay. Initial introductory material over. Let's talk data growth, because this is central to our story. If you're not drowning in data, not a lot of this is going to be relevant for you. But if you're not drowning in data today, you very well may be tomorrow. So this chart is showing data growth over time. For full disclosure, I completely made this up, right? But the underlying trend is real. And the Wall Street Journal, of all places, did this wonderful recent story where they shared, they used an analogy of a single low resolution image as a grain of rice. And then they started to contrast this or show how much data different organizations and companies were generating and how that's changed over time. So over on the left is from a single Major League Baseball game. Major League MLB StatCast now gathers all this data because they can sell it to fans. The teams use it for analytics. There's lots of ways they can make money off of this data. And from a single game, they now generate something like 5 terabytes of data. Okay, that's not crazy. Maybe if you had a really big server, you could start to process that. But of course, there are lots of games, there are lots of teams. See, as time goes on, you have seasons and seasons of data. It's a pretty decent amount of data. When previously, if you're like when I was playing Little League Baseball, we kept score in baseball, right? It was on paper. You could look across your season. This was the amount of data you collected for a game. You dropped little lines, so-and-so Steve got a double, et cetera. Gus struck out. This was a manual small amount of thing. Now they're getting 5 terabytes of data. It's a pretty big increase. Second one, and this one's the extreme example, but is YouTube. And this is what's nuts. This is every day they're gathering something, and I don't know why the Wall Street Journal wrote this as 4,860 terabytes. I think, check me here, webinar audience, that would be almost 5 petabytes of data, but a significant amount of data every day. Now, of course, that's not you, that's not me. We're not generating that much data. We're not processing all of that, but the volumes are huge. And what's really interesting is that daily volume has just been a drastic increase since roughly 2007, 2010, when YouTube first started publicly sharing some of this information on how much data they're collecting. So the data volumes are real. I know you know this, but I just really want to hammer it because we're going to need tools to process it. And I suspect this is not my audience today, but I feel compelled to make this point because I do work for a vendor. And there is an open question that's in the back of the mind of a lot of people I talk to at larger companies and enterprises. And they'll wonder, they may not explicitly say, but they'll wonder, hey, can a vendor save me from this? Do I really need to learn to process all of this? And I want to grab, is this my problem? Do I have to write code? Do I need to write Python? If I do write code, can someone just fix this for me? Can I get an app for that? Is how I would take this question. And so I wanted to bring up a counter argument. My answer is going to be yes, of course. Here at Coiled, we do Dask clusters as a service. We do Dask support. It's all Python. But this New York Times article, the author wrote, by the time, counter to what I'm discussing, by the time you become truly proficient at programming, chances are that whatever you set out to write would be available in some form from a software publisher. Interesting idea, right? So by the time, hey, don't listen to Gus, don't go bother wrangling all this data with code. By the time you actually get good enough at this where you're going to generate business value, someone would have written software. There'll be a startup that's going to solve your problem. It seems compelling, right? And now obviously I'm the one making this argument, but I got something wrong. A critical detail that was wrong about this. I said this January is New York Times. What I meant was actually this article was written in 1984. So when you hear this argument, actually I still hear this come up. This is one of those things that's almost as old as computers. Oh, I really need to bother with this. This is really my problem. Maybe I will say, fortunately, yes, it is. And here's why. That author goes on, and again, this is written in 1984. Computers will become as common to this generation as television was to their parents. But the vast majority of parents do not repair television sets, write for television, or work in the broadcasting industry in any capacity. Why am I hammering this, right? Because what is the huge growth industry of, everyone is working in tech. If you're not working with large volumes of data today, I posit that just like previously, it would have been inconceivable, laughable. Of course, you're not going to work in broadcasting. You don't need to learn how to work with a television set. You don't need to learn a computer. You're not going to work in the computer or tech industry. Hint, yes, of course, probably everyone on this call right now does. Anyone watching this does. Similarly, if you're not working with large volumes of data today, I posit that you soon will be. This is becoming, as these volumes become so huge, the hardware vendors are doing their best, to give us stuff. We can work with everything in memory, but it's simply not going to catch up. It behooves you. So thank you for taking the first step, or the 50th step. You're on the right path. Okay, so I'll conclude this with this holiday season. Give yourself the gift of working with data that doesn't fit on a single machine. It will pay dividends for years and years to come. All right, final 2 words of intro, and we're going to get into some code examples because I'm sure I'm tired of looking at slides. I'm sure you are too. So first up, why Dask? There are many ways that you can run parallel Python. There are a couple of core reasons that come up all the time. One, Dask has a familiar API. What does that mean? Well, look at this code over here. I've got pandas code, which is Nice for creating data frames like spreadsheets in Python, rows and columns. I can read a CSV in Pandas, and I can write this little group by to aggregate the data. Dask also has a data frame. I can do basically the exact same thing, read CSV and group by. Okay, that kind of makes sense. That's a big reason people like Dask. A second one that's really important, I can run Dask on my local machine, like on my MacBook Pro right here. I can scale it out to a cluster. We will cover, by the way, how to do different styles of Dask deployments. Several of you answered my emails about what you wanted to hear in this webinar. I really appreciate it. One theme that came up was talk about how to deploy Dask in these settings. And so I'm definitely going to do that. We'll cover that at the end. And then the third is the integration with the rest of the PyData ecosystem, in particular the Python ecosystem. So Dask is written in pure Python. This is to contrast the little shade at something like Spark, which is written in the JVM and Scala. And so it works really well with other Python stuff. And I'm going to make sure to show those types of examples. So that's maybe why those are kind of the popular reasons for using Dask. Of course, we're going to today dive into industry specific examples, but if you remember those generic reasons, that's a good one. Familiar API, develop locally, work locally, scale a cluster and back, and then integrates really nicely with Python. But if I'm going to make the case why you should use Dask, we should also talk about why not to use Dask, or when not to use Dask, or what you should do before you use Dask. And there are 5 kind of critical things that you should think about. And we'll revisit this at the end. So if you want to touch on this, I will touch on this once more before we leave today. But first up, number 1, before you use Dask, use better algorithms or data structures. Like, what the heck is a better algorithm or data structure? What are you talking about? Well, if you're doing something with numeric Python, you can look in NumPy. NumPy is written in Python, but also in C, C++. There's Fortran code in there. There's a possibility that something in NumPy or SciPy might do exactly what you want to do, and it might work even faster. So do check that out. Second, better file formats. You might be reading, a common use case for Dask is going to be reading in lots of data from a bunch of different machines or from a bunch of different services. You may be reading in data in CSV, and if you simply switch to Parquet, actually this would fit in memory. It would work better, some sort of minimized, chunked format. There's tons of those. Do check that out as well. Third, and this is going to get a little bit trickier, you may want to compile your code. So one of the big complaints against Python, Python's so slow, it's interpreted, but there's this trade-off, it's so easy to use, I mean, relatively speaking. You can get C, C++, Fortran-like speeds with Python if you compile your code. One fun way of doing this is with a JIT compiler, or just-in-time compiler with something like Numba. You can also check out Python, although to me that's beyond my level. Not that my level is much of a level, but that's getting a little trickier. But you can compile your code. You can often see significant speed ups. Fourth, sample your data. So instead of working with all of your data, hey, if there's 5 terabytes of baseball, if 5 terabytes per game, maybe I'm going to look at the first inning or the last inning. Obviously, there's some drawbacks there, but sampling is always a very good strategy for getting stuff to work locally. And then fifth is you want to profile your codes. There are lots of great tools for profiling. If you watched last month's webinar, if you read the work of Ian, he's big into profiling. He'll show you lots of ways to profile your code. And this is a really good way to make sure that you're squeezing everything out of what you got. Now, I mentioned this as why I titled the slide, why not to use Dask. By the way, these are the Dask best practices. If you can see the bottom, this is the source here. So this is actually how you should also use Dask. When possible, we want to use the best algorithms and data structures within Dask. This may mean things like using the Dask data frame collection or not. We want to use good file formats when we can use things like ZAR and Xarray to work with ZAR in the case of, let's say, image files that are going to be chunked. We'll go through these examples. You're going to see a big performance. You can use Numba with Dask. We can compile code. We can send it across the cluster. Lots of fun stuff. We can still sample, and oh boy, can we profile our code with Dask. There's this wonderful Dask dashboard, this bokeh dashboard, so we can get really rich information about what's going on. And if at any time you have a question about that profiling, just send it over to Coiled, send it to your favorite neighborhood Dask sales rep, and we can take a look at it for you. Excellent. So let us now jump into some examples. And actually, I'm sorry, I said final thing before code, but the last thing is across all 3 of these industries and across other tools, we tend to see 3 entry points for Dask. And that means, so if I'm in one of these industries, you typically come into the Dask world if I talk to you, you're using one of 3 interfaces. First, it's big data frames, it's big arrays, it's I'm using scikit-learn's estimator, so I use Dask ML. We'll see an example like that with capital One. I'm using pandas data frame, I use Dask data frame. I'm using NumPy arrays, I like ND arrays, I'm going to use Dask array. Very simple, straightforward. It certainly can get complicated, but that's an easy entry point, you can imagine. The second one maybe is a little surprising, and that's people who are using Dask but may not know it. They may not even know it until something blows up and they get this out of memory error or something like that. Of course, Dask never has errors. You will see this. We'll see this for tools like workflow orchestration tools like Prefect. I'm going to show a quick example with a cell analysis tool for life sciences called Napari. And this is just using Dask under the hood. So as a user, you'll either write some code, or in the case of Napari, you do this with an application. It's using Dask. You don't have to worry about it. You can then scale to a Dask cluster when data gets really big. It's a very nice interplay. This is a very happy path. And then the third one, and the one that I'll probably spend the most time on with my actual code examples, are the lower level interfaces for Dask. So there are two lower level collections where you can start to build your own task graphs, delayed and futures. If I were to look at a Dask data frame, for example, I would see as a collection of futures objects. You could build the other collections with futures. And this will be a lot of fun. So we're going to actually start with these examples. And I will also show people building custom task graphs. There's a wonderful retail bank credit modeling example with Dask that we can look at building a class. We can basically specify a function, inputs, outputs, and let Dask just build this task graph around us. Really, really nice. Okay, so enough of this. Let me jump in and let's look at some code. So before we start, let me go into my view here. Hopefully this simple interface looks okay. And I'm going to jack up the visualization. So, I'm going to take a quick look at the chat. Looks like we've got lots of great comments. Alan Jackson commented about astrophysics data. Yes, there's an AstroPy package. That's awesome. Oh, Ricardo, yeah, IoT data. True, tremendous. And then a product that builds on numbers from Matt, Bodo AI. Yeah, I've heard some interesting things about Bodo for doing big analysis. It's wonderful how many different tools are out there. I don't think I've used Bodo specifically, but I remember Travis or somebody commented on it recently. If you don't work with Dask, you should, Matt. I don't know. We'll see about that. But anyway, let's dive in. I want to show a generic Dask example first. I'm going to make this really, really quick. We're going to build a little bit of intuition around parallel Python with high-level Dask collections and then the lower-level Dask collections, Dask delayed. We need to do this first before we jump into the use cases. Otherwise, I don't think the use cases are going to make any sense. So bear with me on this. If this is review, it'll be fast. Okay, so let's first create a Dask array. And this is similar to a NumPy array. And so I'm going to instantiate one with just 15 random numbers or 15 numbers. And oh, go figure, this is what it looks like. I'm going to call this visualize method. And so what I have here is just some data that could be sitting in memory. In this case, Dask is lazily executed. But my task graph, this is really unimpressive. It's just a single task. It's not parallel. It doesn't help me. So what you'll often have, or what you'll often do, is you'll have this data chunked up where you'll have multiple tasks. And I can now take that same array, split it into 3 chunks. And now I have 3 tasks. Wonderful, right? I can execute these in parallel. Now, the chunk sizes, partitions, these things become extremely important when we're working with collections like arrays and data frames, because they're going to help dictate like how many things we can run in parallel, how this is going to work. But at a very basic level, right? If I have a single task, I'm running one thing. If I've got multiple tasks, I can potentially run them in parallel. So let's do an actual computation. Let's sum this array. And when I do this, I'll now visualize it. And what you can see is that we have our 3 steps. Each of these chunks is going to get summed, and then it will combine into one aggregation. And I know this is maybe a little weird to see it because I've zoomed in. It's a little bit better when it's wide, but hey, that's the idea, right? We're now doing this operation in parallel. Each chunk has its own sum step, and then they're all combined at the end. Did I write this? Did I tell Dask to build this? No. I just said, hey, take this array and sum it all up. And it figured out, okay, great. I'm going to be smart. I'm going to use the code that the wonderful open source Dask developers have developed to perform this. I'm going to execute this task graph. I build the task graph, and then when we run it, we'll execute it. Now, of course, things can quickly get much more complicated. So let's build a 2-dimensional array, and let's visualize this same sum. Now we're at something that's looking a little bit more intimidating. Like maybe you could have built the previous one, but perhaps you don't want to build this sort of task graph by hand with Python code. Let's add the array to its transpose. And now you can see that Dask is just, again, automatically, we're visualizing here, we're seeing the task graph that's getting built. This is starting to get more complex, even more complex. Dask is figuring out which tasks can be run in parallel and which can't. It's building this task graph for us. I'm going to extend this further. So if you're not disgusted already, it's going to get worse. Let's go ahead and add in a matrix multiply. And now our task graph looks like this. Again, I just say for these type of basic operations, you could build this out manually. You could create your own tasks. You don't necessarily need to use something like Dask, but this high level collection works really nicely for figuring out what can run in parallel and what can't. And this is what it looks like. This is what's going to get executed. And then finally, just for one more of these for giggles, let's throw in a mean to our matrix multiply. And this is what we end up with. So excellent, right? Hopefully this is building. So what does Dask do? Well, Dask gives us these collections for building and executing task graphs. And it will, when I use a high level collection like data frame, array, Dask ML for estimators, it will build these things for me. So that's one level. Now the second level of this is the lower level interface for Dask. And I suspect that basically, and the reason why I'll pause here to emphasize this is, if you find yourself with an array, with a data frame, with an estimator, you can more or less swap in Dask, the Dask version of that object or that collection, Dask collection for pandas data frame, Dask collection for NumPy array, and Dask will build these task graphs, and you could see if it helps. You can see if it works. You don't really need to dive too much into what's going on. However, what I often find, in addition to that, it's not however, in addition to that, it's very likely that a lot of the problems you're going to be facing in doing quantitative things and wherever you're doing them will look less like a data frame and an array and more like some functions that you're applying to a bunch of stuff. Functions to a bunch of stuff. And so let's show a generic example of this, because this is highly relevant, because I'm going to be showing you a specific example of this in a second with a Monte Carlo simulation. So if you can follow this, you'll follow the Monte Carlo one. So let's define 3 arbitrary functions: increment, double, and add. And we've got a list of data, we've got some data, and we're going to run over this list our 3 functions. We can run this serially, and it would take some amount of time. In this case, it's going to execute boom, boom, boom. If we threw like a 1 second sleep in here, we would see this added 1 second, 1 second, 1 second. Okay, fine, who cares? Instead, what I want to do is I want this to run in parallel. I don't want to build the task graph. I just want Dask, I want to tell Dask, build a task graph for my existing functions. So I'm going to take that exact same code. Actually, let's make sure I actually ran all this stuff. And I'm going to wrap this same for loop with Dask delayed. And when I do this, I'm going to say, hey, I want you to run that increment function. It takes X as its input. Increment, so increment X, and then double X. So we'll call delayed, we'll wrap double and X. And then finally, we'll call the add function, which takes the inputs of now A and B, the outputs of these two. And at the end of all of this, we instantiated this empty list. We're going to append our outputs to the list. And then we're going to sum all of this. And again, I can go from sum output with Dask delayed, sum, and output. Okay, so what is this going to look like? What is the task graph that Dask is going to build? Well, if I were doing this manually, I would see, for example, that increment and double, they do not have a dependency on each other. These could run in parallel, but this function here, this output C, it's dependent on A and B. Dask is very smart. It figures this out. So here's what our task graph looks like. Here's what's going to get executed in parallel. The increment and double steps will run at the same time. They're a dependency for add, and then all of this is a dependency for the sum calculation at the very end. Now, I know this is generic, and the whole point of this webinar is to get into industry-specific examples. So I hate to spend time on this, but it is absolutely critical. So if we get this intuition around, thinking about, like, I've got some data, I'm applying some sort of costly thing to it, I can just loop through. This is one, I think, an area of, dare I say, low-hanging fruit for you all. And at the end of all of this, if I just want to return what the actual value is, you're like, hey, you're showing me a lot of task graphs, but I'm never going to get an answer. I could call a method like compute to return it locally, or persist to persist it to the cluster, and I'll get back the actual value. So with that, I'm going to jump over, and we're going to now go back to slides very briefly, and we're going to talk. Let me go into presentation mode here. And we're going to talk about some specific examples we're going to start with finance, and then I'll show some code, and then we'll do the same for life science and for energy. I will quickly check the comments. No new comments. Maybe I've bored everyone. I've stifled them. If you've used, I'll go ahead and just ask a quick question. If you've used delayed or futures, let me know, please. All right. Now let's talk finance. So I kept this interactive. I typed a question in the chat. So Dask and finance. Oh boy. Python is big in finance. You know, pandas, Wes McKinney wrote pandas, as many know, while he was at a hedge fund, I think AQR Capital Management. So if you're working with time series data, which you probably are, securities, things like that, whatever it may be, you're getting lots of tabular data, lots of Excel style stuff. Pandas, of course, is big, and thus Dask is very, very big. So the typical use cases we tend to see: backtesting, simulation, risk modeling, even, dare I say, kind of the holy grail for the AI startups, which is not us, these end-to-end ML workflows. Capital One has a wonderful public example of this. So we even see some of that. The data formats we tend to run into, no surprise here, n-dimensional arrays with stuff like NumPy and then pandas for data frames. The professions, I think this may be a little bit interesting to folks. So the people that we tend to talk to who are Dask users it's very bifurcated. There'll be the quant or the quant researcher. Maybe those are kind of the same, sometimes also called portfolio manager if it's specific to, let's say, a hedge fund. And then often the person managing the Dask environment is a software engineer. So there'll be some sort of engineer who's in charge with managing the infrastructure. And these are two distinct people, and they'll obviously report to different parts of the business, engineer up through IT. Infrastructure is very, very interesting here. We see a lot of on-prem, maybe not surprising for something like finance, but with a fair number of cloud deployments, particularly on Kubernetes and the managed Kubernetes services that are offered in the various clouds. And we still see a little bit of HPC usage, the high performance clusters, which again tend to be on-prem. Let me shift here. There we go. So what types, let's dive into these use cases. Let me show some fun examples. So the kind of the predominant use case we see with Dask are sorts of tasks that could be bucketed or summarized as embarrassingly parallel, kind of like we saw in the example before, where we had this for loop, and here's a different view of that step with these various functions that aren't dependent on each other. And this could be as simple as something like, I hear all the time, if we're a fund, we download data from a myriad of different sources. We've got 25, 30 different data providers that we pay. And we may use something like Dask, just do these big data downloads, and then some of the transformations on these ETL jobs. No machine learning, no AI, just download data, do some transformations, write it into our object store, do this with Dask because we just want this to run in parallel. We want it to run fast. Similarly, we see lots of fun examples with whether it's in risk analysis or portfolio optimization, we're just running tons of simulations. And I want to show you one of those right now, doing a Monte Carlo analysis for option pricing. So let me stop sharing. Oops, I did not mean to, I meant to continue to share. I'm sorry. Oh my goodness, how bad of me. Apologies, 1 second. Let me go back. What I meant to do here. I'm so sorry. Oh boy, that was bad of me. All right. Apologies for the technical difficulties. Okay, let us go and look at some code. So hopefully, actually, Christiana, could you just tell me maybe in the chat or something if you can see my screen, or if anyone could?
You're good. Yeah.
Good. Okay, great. Thank you. Thank you so much.
No
All right. Let's jump out of simple interface. Thank you, Sammy. Let's go over now and let's look at this. Let me go back into simple interface here. Hopefully it's a little cleaner. Great. So what we're going to do now, and just as by way of introduction, is we want to do an embarrassingly parallel task. We're going to take a costly simulation, and in the finance domain, one that we see all the time is a Monte Carlo simulation, which is drawing a distribution, we're going to generate a bunch of random samples, and then we're going to run some sort of mathematical formula. And the mathematical formula we're going to run is the oh gosh, I hope I pronounced this right. Otherwise, you can tell what a dilettante I am. The Black-Scholes model. And in order to do this, first, I just want to tell you we're going to create a local Dask cluster. I'm running this on my local machine. See, I'm not shilling for Coiled here, right? This is, I'm gonna run this locally. Anybody could do this. And I've got this local client here. So this is just Dask running on my local machine, 12 threads, 4 workers. I could customize this. And so what we want to do is we've got this function defined, or I've got it defined, to do this option pricing, to tell us, okay, what is the value of this option, which is this contract that has a future date of expiration? What is it worth today? We'll define some inputs and we'll come up with this formula. And just by way, so you know, I didn't write this like from the back of my head. Well, another author that I love, if you follow the guy who wrote the book on Dask for Finance, Yves Hilpish, he recently wrote a new book called Financial Theory with Python that I really like, where he maybe instead of giving you these, just hammering you with these wonderful, you know, Python examples for finance, he goes through and explains some of the financial theory. So, you know, maybe if you were an English major, like somebody, it's very helpful for getting some of the math and seeing Python that you can then run to try to figure this out. So thank you, Yves. This example is from him. The application to Dask is mine. So if you hate it, I'm not saying he did this. But in this case, we've got this formula. We could consider this, for all intents and purposes, to be a black box. Let's go ahead and just run it one time locally, where we're going to run through what is 100,000 simulations with these inputs, and we get back a result. Here's the price of the option. Okay, great. That's all well and good. But what the goal here is to say, okay, well, what if I want to do either additional simulations, or I don't have fixed values for any of these inputs? What if I have, which is likely, tons and tons of, I want to run this simulation at 1 million different initial pricing levels, at 1 million different strike prices, at 1 million different times to maturity. I want to step through all of this. And I'm going to show you a very basic version of this, where we're going to take the measure of volatility, excuse me, we're going to take the measure of volatility sigma, and I'm just going to build a small list here. And so very, very similarly here, I'm going to say, let's run that same Monte Carlo analysis, that do the same option pricing, but now we'll run it over 5 of these volatility weights or settings instead of just 1. Now, of course, 5, this isn't going to be required Dask. This is just meant to be an illustrative example. But what I hope you see here is we have an empty list. We're going to loop through and a list of values. We're going to run Dask delayed on our costly simulation function, which before, remember, this was inc, it was add, it was it was that hypothetical thing. Now it's something real. And then we're going to append those results to our list. And let's go ahead and run this right now. And this code will execute very quickly because Dask isn't doing anything. I'm sorry, it's not actually computing anything. It's building the task graph. And so if we look at our task graph, let's look at the first one of these. I'll grab the first element of this list. And as an aside, you're seeing that these lower level interfaces, like this Dask delayed object, it's Python, so I can add it. It's an element of the list. I can index the list just like if it was anything else. And so I can look at this, and here's my individual Monte Carlo analysis. Now, also, just like before, a single task, it doesn't help us, right? We want to run this thing in parallel. We want lots of these to run at once because they're independent. Each Monte Carlo simulation doesn't depend on the last one. So I'm going to then and I'll take all of my results here from this list, and we're just going to average them. And so now let's visualize this to see what our task graph looks like. This is not high finance. This is not something, it's not by no means financial advice, right? I'm not saying that a quant is doing exactly this, but generically, this is the idea, right? Now I have, instead of just one, or we're looping through in serial, running the simulation over and over, or each of these 100,000 simulations over and over again, I can run them in parallel. I have 5 here, but I could have many, many more. I could be looping through data frames with many columns. So each of those inputs could be its own column with a bunch of different tasks, and Dask will build out this task graph for me. I just added delayed to my little for loop, and I can see how it goes. And then we can compute this, or we can call compute on the total, for example. We can compute these individually, compute the total, and I get my result. Here's the average option price. So, oh boy, I'm taking up a lot of time here. I'll speed things up here, but I hope this should be a representative example that we're going to see in other domains too. I've got some set of data. I want to apply some sort of scientific, quantitative, costly function to it. Monte Carlo simulation for option pricing, great. Single cell analysis, a genomics thing, wonderful. Seismic data analysis. If you have the code, you can use something like Dask to apply it and run it in parallel. Good. Okay, let's go back now to our slides, and I'm going to, instead of going into the presentation mode. The next one I want to show is a more complex credit risk modeling task. And it would not be good if I only showed you this basic stuff. I got to show you some of the more complicated things that you can see. And this is an old example, but still a very relevant one. And this was from a blog post written by Rich Postolick when he was I believe at Anaconda at the time. I think I was there too. And this was representative of a retail bank example he was working on with Dask. And what we want to do is we're going to take a population of applicants. We're going to try to model who's going to default. And we'll do this with some simulated data that he provided, which is nice. But more importantly, it's the building this. We're going to start to build out this task graph. We're going to say, okay, what I really want to do is I know the thing that I want to create is maybe complicated. I just want to specify, here's the function right here. Like, here's my default function. Here's what it's going to take. Here's what it's going to return. I don't want to repeat the computation. Dask, you figure out how to make this run in parallel. So let's jump into this. So I'm going to jump in here to I'm going to create some data. This will be representative of the incomes and the credit histories of the people. And let's say this is let's say this is our default function. So a little bit generic. The interesting thing here is we could take something like this, and this is a function that has multiple steps. We're incrementing. We're going to divide by 2. We're having the data. We're also taking the exponent and adding it to the result here. If we split something like this up into individual delayed functions, this is a kind of a crux, like low-level idea. We can split this up. Dask will now be it'll be much easier for Dask to build this complex graph for us. So I'll go ahead and do that here, going from basically something that's your standard Python thing, a slightly more complex function, and we're going to split it up into individual delayed functions. We're then going to run that over our 2 data sets. And to make this a bit more realistic, we could just run sum on this final list here, but we're not going to do that because I would be cheating. Instead, we're going to use a slightly more complicated merge function that will scale better. So we'll sum as we go across this data set. And when we do this, we can visualize, I'm going to skip ahead to our average default here, what this looks like. And this is the task graph that Dask is building for us. So I had an increment, a have function. We then combined them, we aggregated them. Dask built this complex task graph for a costly simulation. We're not repeating computations we don't have to. This is happening automatically. And this is coming again from a real example at a retail bank. They're able to do this. And the way they implement this specifically is defining their own custom data structures. So this is even slightly more low level, but they would define like a class, for example, for default. They'll wrap that same function with delayed. And again, this is what this is going to allow them to do. I just said, hey, here's the order. I want to run this function. This is the input. That's the output. Dask then figures out what the task graph is going to need to be, what's the most efficient option for parallelization. So wonderful. We've got that. Now let's talk about, I've taken a little too much time. Let's talk different use cases. I will say one brief word here about Capital One, because they have so much good information. They've got a ton of great stuff on their blog. They use Dask all over the place, small data sets, data with a few columns to tons of columns. They have some end-to-end workflows you can see Dask used throughout kind of an end-to-end ML workflow. They'll use collections like data frames, like Dask ML, like Dask XGBoost. They have one great example with something like a 90x reduction in time, 2 weeks to a couple of hours for an end-to-end ML workflow using XGBoost with Dask, with GPUs. And in particular, they also they add their business logic into their PyData stack. Mike McCarty, who now works at NVIDIA, he wrote a great blog post that I've linked here on how they extend scikit-learn with Dask and Rapid. So they add in business logic for some of their transformations directly into the scikit-learn or via an extension, so that you don't, what may happen is somebody's like, oh, I've customized this estimator, I've checked this into Git, 4 years later, somebody uses it and they can't understand what the changes were made. In this way, it becomes much more reproducible and easier to share. So that'll be it for finance. We saw embarrassingly parallel, we saw custom task graphs, and then for a good example of an organization that loves to talk about Dask and how they use it in a lot of different places, Capital One is your place to go. I will briefly check the chat here. Alan says, hey, you weren't showing the Dask dashboard. You're so right, Alan. I'm sorry. I should have been showing the Dask dashboard for those examples. So you could have seen the task being processed. That's all about profiling. It's step 5 of the best practices, and I didn't do it. I apologize, everyone. Maybe we'll get back to that maybe at the end if I can stop talking and show you some more examples. All right, let's switch gears here and let's talk Dask in life science. So what are the use cases we tend to see? A lot of things based on microscopy or the images that come from microscopes. So there'll be a ton of image segmentation, image processing, as well as topics around single cell analysis. And then I think broadly, the third category would be stuff like genomics, genetic analysis, statistical genetics. You can tell I understand this really, really well, right? What's fun is the data formats is another thing that's interesting. There's a ton of image data, and this image data is often stored on disk in a bunch of small files. So it can be relatively easy to load a single or individual image, like the grain of rice from our Wall Street Journal example, but processing all of this image data can be a real pain. And that's where data formats like ZAR, we'll see, and we'll see this example with stuff that's built into Napari, but Dask can be really helpful for this kind of one-time computation of like, well, I just need to transform this data into a chunked file format so that I can do parallel reads much, much faster. For single cell analysis, a common data format is annotated data or AND data. And in particular, there's a recent Dask project that uses Dask to extend that, which is great. And then for things like genomics or genomics data, we'll see formats like VCF. And those will often, again, similar to the image data, be transformed into something called ZAR, which is a better storage format or chunked storage format for these types of files. The professions we'll see, it depends on how big of a company. At a really big company, we'll hear titles like computational biologist or computational chemist. I mean, and at smaller biotech startups too. These people often have at a smaller company an asterisk on their title. They're a computational biologist and data scientist and cloud architect and sysadmin running all things. So a kind of a pattern we tend to see at a smaller kind of biotech startup with something like one person is in the wet lab doing an experiment. They're doing stuff. They're sending data back to the person who's crunching it, running Dask on their local machine or on a big server or on a cluster, and they're returning results and then communicating back to the person in the lab. Okay, here's the result of the thing you just did. Now you can try X. So that's sort of iterative process. So the data volumes may not even be huge, but when stuff comes off the experiment, somebody's crunching it, and especially when they're early on, it's actually a manual process of doing the analysis and sending back the results. In the future, of course, software could all be automated, but it's kind of cool to see that as like, well, what's the driver? Well, like how long can the person in the lab before they get bored or before they have to go home for the day? In infrastructure, we tend to see a lot of on-prem, especially first, just, hey, I run this on my local machine. It previously ran in 45 minutes with using, if I have a data frame with using something like pandas. With Dask, it now runs in 8 minutes. Maybe with Coiled, it runs in a minute or something like that. But they're able to run very, very efficiently on a local machine. And then we do see a decent amount of cloud usage, especially in AWS and GCP. Okay, so what are the types of code examples? Let's look at some of this. The first one, this is a good life sciences provides, and a lot of this I should say is available or is easily, we can find this very easily thanks in no small part to Genevieve Buckley and the work that she's done with the Dask project as part of a life sciences grant. So big thank you, Genevieve. And some of the projects that she's collected and highlighted and helped, marshal development resources for, use Dask under the hood. So what you're looking at over on the left is Napari. Napari is a desktop application for doing this cell analysis. It also has a Python client. For single cell analysis is this tool SquidPy, and then for statistical genetics, SGKit. What's really nice about all of these is when you use them, and here's a little Napari code right here using Napari, and in particular a tool called Dask Image, you're using either a local or remote Dask cluster under the hood. You can make that decision, of course, if you want to swap out the cluster, but you're using Dask under the hood, you don't have to care. And this is ideal, right? So that no one has to think about their task graph unless you want to. You don't have to think about your distributed data frame unless you want to. The software just takes care of it for you. So you can read in this image, and then you can see it visualized in Napari over here on the right with this cool little GIF. And for what the science is here, I pleading ignorance, I'm rapidly trying to get up to speed as best I can. That's cool for stuff where things are built in. That is rare, not rarely, but that is never going to be the case. And so I previously we saw the example of the Monte Carlo simulation for finance was like costly simulation. Let me just wrap this in a loop. I've got this in a loop. Can I apply Dask to it? Well, a really cool example I saw on GitHub today is using a tool called Cell Profiler, which is an open source application, another visual application, desktop application for doing cell image analysis. And what this person did was it's an actual executable, it's an exe file. They wrapped this executable with a for loop. They went to their HPC clusters, their big high performance cluster. If your IT department has one of those and you can use it, you could do something like this too. So they get their Dask cluster, it's running on this big HPC. And they just use a map function. This is the features interface of Dask to map that executable with a few arguments across the cluster. And this is me modifying the code a little bit. So this is a little bit of pseudocode, I apologize. But this is, it's something that you very much could run. They loop over those futures as they get executed and return the results and append them to a list. So basically it's like, I've got this exe, I've got this thing, it's not even Python. I'm going to split this up on all the workers in my cluster or on some number of workers in my cluster. I'm going to pass in some arguments. I'm going to use Dask and Python to just execute this, with the sub-process module in Python just for executing, system commands. So I thought this was really cool. I'm not saying that this is amazingly high performance, but basically you could take, the implication here, right, is you could take almost anything, any program, run it over a cluster using something like Dask. So I know I talked about like profiling your code and doing all these cool things to make sure you're squeezing everything out of all out of what you've got. You can also just go the other direction too, right? Just grab something and run it and see how it works. Okay, next up here is going to be oil and gas. We'll jump back over to a notebook here in a second. And so for oil and gas, we tend to see data sources. The two big data sources we see in energy are seismic data analysis and well log data. The data formats are very interesting. This was new to me, SegY, so that's how it's pronounced. I wanted to call it SegY, but it's SegY data and stuff like X-array, which is another kind of n-dimensional array format. X-array is great because it has a native Dask integration. And the professions we see here are people who work as geophysicists or computational geologists. And what's interesting from an infrastructure perspective is, especially at some of the larger the names you'd recognize, they tend to have big HPC clusters as well as a strong on-prem footprint. So people will get, a big machine with a bunch of GPU cards on it, for an example. We see a lot less cloud here. So this is kind of a stack rank list. I got a big HPC cluster. I've got some servers on-prem. I have a lot less of cloud options. And oops, let me pause. Let's just show a quick, actually, you know what? With time remaining, I'm sorry. I'm going to skip this example. We can link to it later, but they're just, it's following the same pattern we've seen before. We can go grab data. We can read it in parallel. We can run costly simulations. We can wrap all of this with Dask. And then when we have things like data that gets into a format like X-array, we can use an existing Dask cluster and just do our array manipulations, just like it were a Dask array or a Dask data frame, and not have to care about the task graph. Apologies, I didn't manage my time well, but we'll move on. So to wrap this up, hopefully you're feeling somewhat motivated, like, okay, if I work in one of these domains, I can apply some existing code that people have written in Python or not via Dask. Where do I get a Dask cluster? And this came up when I just kind of informally surveyed people who signed up for this webinar. This came up a couple times as a question, so I do want to touch on it. Jacob Tomlinson works in NVIDIA. He's spends most of his time or all of his time on open source. If you file an issue with one of the many Dask projects for deploying Dask in the cloud and Kubernetes, it's likely Jacob may be the person to answer you or help you. And so from a recent tweet this year, he wrote, Dask gets deployed in lots of ways. We're going to bucket those into three main categories. And that will be first, your local machine. You can always run Dask locally, both in the single machine or with the distributed scheduler running locally. Then whatever cluster your IT organization gives you. So if you're small enough to have your own IT, you can do your own thing. You've got a lot of options. But most of the people we talk to, IT says, here's what you have. You can use this in the cloud. You can use Kubernetes. You can use HPC. You can use Yarn. That's how you'll get started. And then the next step will be to use something like a managed service. We'll talk about those. This is where Coiled will come into the picture. But first up, yes. Oh, and I see in the chat, Can you post links and titles on the textbooks? Yes, absolutely. Are there documented best practices on Dask on Docker or applications not use Kubernetes? That is yes, there are, but if you're running on just Docker but not Kubernetes, you probably aren't benefiting from the scale from a cluster. So we need to unpack that question a little bit more. But you should find for that recent question, you should find this section very helpful. So if you're getting started, the first thing you should do is run Dask locally. You could do this on your local machine or locally inside of something like you could run this in a Docker container. This will let you take advantage of all of the cores on whatever server you're running this. Laptop, Docker image, running on a big server. So for an example, if you don't have Kubernetes and you can get a big server with 64 cores, you might use something like Docker or just install Dask manually on that server and take advantage of the 64 cores. Similarly, if IT gives you, this is maybe less common, a bunch of servers, you could then use something like Dask SSH to create a Dask cluster on the servers, passing in the IP addresses. That's maybe not the case for a lot of people here. If you have an HPC cluster, PBS, Slurm, LSF, you can use Dask job queue to create a Dask cluster on your HPC environment. If you have a Yarn cluster, CDP, HTTP, EMR, Dataproc, you can create a Dask cluster on your Yarn environment. Maybe not that much fun, but you can do it. If you have Kubernetes, you can Helm install Dask on Kubernetes. And then if you just have access, if you have some sort of cloud credentials, you could use a tool like Dask Cloud Provider to stand up individual clusters in AWS, Azure, and GCP. I should continue, but I see Matt asked a question. Can you run on a Databricks cluster? Matt, yes, you can. Is it recommended? Is it supported? Well, it's not supported by Databricks, but you can absolutely do it. And I've talked to people who've done this. They use the init scripts in Databricks. They install a scheduler and on their workers. If you do it, and I would ask you to just let me know. Maybe I won't give you a book or anything unless you really want one. But if you're out there and you run Dask on a Databricks cluster, do please let me know. I'm always fascinated. I hear this maybe more often than one should, and I'm very curious. But yes, you absolutely can. Init scripts in Python are your way to go. If you do this though, and your IT yell, and the experience is awful, don't say I told you. Okay, so that's how you'll get started. That's how to get a cluster. Dask Cloud Provider for your first Dask cluster in the cloud, as an example. If you have a team of people, if you want a Dask cluster for more than one person, it's very likely you'll pick an open source alternative like Dask Gateway, or you'll look to a vendor for a Dask cluster as a service. Because now things like authentication, authorization, cost control, logging become important. So I highly encourage you to check out Dask Gateway. Dask Gateway is a gateway server that you can stand up in your environment. The backend, as a user, I will authenticate to the gateway server, and then I can create my own Dask clusters on Kubernetes, HPC, wherever the admin can configure the backend here. So there's more work. If you go with the Dask Gateway route, this is good software. You will kind of have to allocate part of your time as the Dask Gateway admin. If you don't want to do that, or as an alternative or in addition, you could use something like Coiled. So here's a little bit of sample code here. I pip install the Coiled package. I authenticate to Coiled, and then I can just create these Dask clusters on Coiled, specifying, hey, I want this number of workers. I want them to have GPUs. I want to use this software environment. So you've got lots of options for getting Dask clusters. And just to kind of quickly recap this, it's, hey, getting started locally, always pip install or conda install Dask distributed, run locally. You've got options, Kubernetes, Dask Job Queue, Dask Cloud Provider. If you have access to those environments to get individual clusters, generally speaking for you. If you're thinking about a team, something like Dask Gateway is a really good option. And then you could also look to vendors, again, Coiled, come talk to me, Gus at coiled.io. Love to tell you more about it. As we wrap this up, at the beginning, we said, I gave you this kind of disclaimer about like the best, when not to use Dask, AKA the Dask best practices. I'm going to amend that here with, you can use better algorithms, you can use better file formats, you can compile, you can sample, you can profile, and you should do all of those things. And I should have shown you the profiler for Dask distributed, shame on me for not doing it. But you also have this option here. I'm going to add this. This is Gus number 6, not a best practice, grip it and rip it. Let the big dog eat. Just go get a big cluster of machines, wrap that little, take your for loop, wrap it with delayed or futures, and just see what happens. And if the cost and the time spent to get a cluster is low, like if you use something like Coiled, it very much will be. It's very easy. It's very inexpensive. You can then just try it. And then you can go back and maybe find a better data structure. You can figure out a better format you can compile, but you can also just see if it was worthwhile. What would happen if I ran this on a cluster with 3 terabytes of RAM? Maybe that's a lot for you. Maybe it's not. Maybe what would happen if I ran this across 1,000 cores? Just go to Coiled, get a big cluster, try it out, see where it goes. And if you want to try that out, you can get started, coiled.io, contact us, or cloud.coiled.io, sign up. And since I do work in sales for Coiled, if you attended this, we have a free tier, which will be in automatically, but I'll give you more free credits. So just message me and say, hey, I sat through your really boring webinar, or I watched a replay of it. I want more free credits. You've earned them. You've earned them. So let me know. And with that, I will conclude. Right on time. Right on time.
Perfect timing. Impressive, Gus.
Skipping a third of my examples, at least the code examples. So I apologize, but thank you, Christiana. I accept that all the same.
Absolutely. Yeah. Well, thank you so much for spending the last hour with all of us. And thank you to everybody who's watching for doing the same. Yeah, people are saying great talk and thank you. So if you're not seeing that, Gus, everyone says thank you. And thank you all. Yeah, thank you all for being here. I will send out a follow-up email with the recording of this and also all of the books that Gus mentioned. And again, yeah, Gus at coiled.io. If you want to chat with Gus, give him a follow on LinkedIn. And also we have if you want to chat with more of the Coiled team, we have a great community Slack that you are welcome to join. And I will link that in the email as well. So yeah, that's it. We're good. We're golden. Thank you for coming to the last Coiled webinar of the year. Gus, thanks for closing us out. It was a good one.
Thanks so much for having me. Thanks for being here.
Absolutely. All right. Have a good one, everybody. See you later. Thanks, Gus.